So welcome to the pre-recording of the third and last part of lecture 6, scheduled for the beginning of the third week in the 8-week summer course on computer algorithms. So we considered in this lecture 3 different problems, but in the algorithm analysis, the 3 type of algorithms are the 3 different type of problems are solved by the same type of greedy algorithm. So the algorithms themselves are very straightforward. Proving the optimality is not. And that's actually the main point of the lecture. So the third problem that we consider is given a weighted directed graph, compute all paths, all shortest paths from a given vertex. For unweighted, undirected graphs, we have considered the breadth-first search algorithm. That actually does this. So in some sense, the shortest paths can be considered as an extension for this. Okay, let's specify what is the problem. So we have a weighted directed graph. Which means that every edge has a direction. So if you list a tuple uv for u and v being vertices, if u comes first, means that there is an edge from u to v. Not necessarily the way back. So it could be that also there is v, u in the edge list, but that should be explicitly stated. Here, every edge, so we are working with a weighted graph. Every edge has a weight, or actually has a length. By using the word length, we will therefore, using the word length implies that that is a positive number. So we work with distances. That's alternative. So we will compute for every vertex in the graph, we will compute a number, and that number is the distance of the shortest path. So of all possible paths from a start vertex to that vertex that we consider. Other way saying, if we have a whole network and there's one source, what is the shortest distance from the source to every other point in the network? Okay, here is now the greedy algorithm. The greedy algorithm assumes that you have solved this problem already for a subset of the vertex set, and you have to decide what is the next vertex that is closer to the source. So actually the subsets is characterized by all the vertices that are closer to the source than all the other vertices not in the set S. So we have already computed, solved this problem, so you will see that we will also prove the optimality via induction. So then the greedy algorithm looks for that vertex to add to our set S, for which the length of, for which there is an edge, so for which there is an edge from some vertex in the set S to V, and where the distance of u to the source plus the length of that edge is minimal over all possible u's that you could take in the set S for which there is an edge to V. So that's how you should read this formula. So we set as the next distance of the next vertex we compute. So V is a vertex that has not yet been explored. So in that set S, we know for all the vertices, U in that set, we know the shortest path, the length of the shortest path to the source. We look at all these vertices U, for which there is an edge to V, and for which the sum of the distance, the shortest distance of u to the source, plus the length of that edge uv, is actually minimal. So that's a local optimization step. So the greedy algorithm is going to greedily add more and more vertices to the set of vertices. At the end, we will have every vertex in the set. Okay, here is the algorithm again. So by doing this, you can see that the length of the shortest path for the new vertex v, that is actually the length of that edge that you considered from any vertex u in the set S to v, and the distance of u to the start vertex. So you look actually to all the neighbors of v, and you want that neighbor that is closest to the start vertex, but also you want to take into account the length to that neighbor. So in some sense, the why this is such a good idea, you don't have to do that many work. So you only have to look at all the neighbors that are inside the set S and check the sum of the length with the distance that you have already computed for all the points in S. Okay, so here now the pseudocode formulation. We have a weighted directed graph. So the weights are the lengths, positive numbers. For every vertex, for every edge, we have a number. We also have given a start vertex, and we will compute an array of numbers, and for every vertex, that array will contain the distance from the source to that vertex. Here you see the algorithm. It essentially applies the mathematical formula in the main loop. So we initialize, and then as long as the set S is not the entire vertex set, we take a vertex that we have not yet processed. We look for all the edges that end in that vertex, if there and is, and we compute the distances, the length of that edge u to v, where u is a point in the set S. So that will be the d prime, and actually we select that vertex. Actually, we want to know the vertex, and we want that first vertex. We can see that in the next example that we will give, we will show that there can be ambiguity, that there can be multiple vertices with the same distance. And then you just select the first one. Okay, so the algorithm is very simple. Again, executing Dijkstra's algorithm is actually not that hard, and also please do it, but you won't get that much credit for it. The main point of this lecture is actually to understand why this is an optimal algorithm. Okay, so here is again to emphasize the parsing of this formula. Perhaps look at the picture first. We have already computed S. So S contains the source and the vertices u and v. So we first picked u, then we picked v. So the distance from u and v, they were direct neighbors. So we picked the closest neighbors to the source first. Now we have x, y, and z. Which one will be added next to the set? Well, I should pause a little bit. I think it should be obvious from the picture that if you add x, then there is a path from S to U of length 1, a path from U to X of length 1, total length 2. And that is smaller than any paths that you can make to Y or Z. I hope that this is clear. The other point is that the distance for X is the same as the distance to V. So in some sense, in the second step, there is some choice here. You could pick X or you pick V. Here is the running then on the algorithm on the same example, but now I'm assuming that there is a sequence of 6 vertices. And here you see the input. So if you ever would need to have a question run Dijkstra's algorithm on an example, this would be the input. The graph would typically not be drawn. So you would need to draw the, or imagine in your head, you would need to imagine the drawing of the graph. Drawing of the graph would be the first example. First step in running the example. So here you see the initialization. The set S is the source, distance 0. Then we select U. I emphasized in thick red the edge that was selected. U is a direct neighbor. We should have considered X and V as well, but X and V, they both are at a farther distance, so it's obvious they are not selected. For the next step, there step 1, step 2. Okay, so there's still a typo on the slides. This is annoying. So here, I mean, perhaps I wanted to indicate that there was a choice, but in step 2, we are not going to select X. V is the first vertex at which this is occurring. So we are processing the vertex list as it is given in order. Okay, step 3, then X comes in, so that was the snapshot scenario. Then in the next step, step 4, we have that Y is added. So you can see the length of the path when we talked about breadth first search, which were unweighted, undirected graph. We counted the number of edges in the path. Here actually we add up the sum. So you can see that the path from the source to Y has 3 edges, and that total distance is 3. You could do with 2 edges, but that would give you a distance of 4. Okay, so we have our last vertex to consider, Z. In fact, the only thing that you might be interested here is which path that you take. And the distance will be 4 because you will also have to run through X. So you have here also a shortest path, which contains more nodes than the path that would run through V. So that's an important distinction again with the breadth first search algorithm that we considered for the unweighted, undirected graphs. Okay, so I hope the algorithm is clear now. The interesting part here already is that there is some choice here. Now, whether you compute V or X first, it doesn't really matter. But you can see that is there an optimal solution? Yes, there is. Will Dijkstra's algorithm always find it? Okay, whenever we have an algorithm, we have to verify the properties. And the first property is always, does it terminate? And actually here, the point of this exercise is that there is somewhere an implicit assumption that was made on the graph. And I came to this exercise actually by implementing this algorithm and running this on random graphs. And of course, I got unlucky and I got a random graph for which it didn't terminate. Now, what was wrong with that graph? That graph was not connected. You see that the stopping criteria, I mean, I invite you back to travel back. So let's see if I can do this. Um, and the algorithm, perhaps. No, it probably, well, I'm getting. So here is the algorithm again. So let me now go to single page. You see that the algorithm stops when the set S is equal to the vertex set. If that is not the case, then it continues. But the point is that there is a problem when there is no edge that can be selected. So here you may not find such vertex. So the algorithm actually implicitly, so the algorithm implicitly assumes that the graph is connected. And that was also the case in the example. But for the exercise, you explicitly have to remove that assumption. And actually, you can modify the algorithm by checking in every step the size S should grow. If that size of S does not grow, if you can't find the next vertex to connect, then also you should stop. It's an obvious thing to do. But again, if you are implementing algorithms and work with graphs that are a little bit too sparse, you may run into this trouble. It's not a trouble if you are in a modern country where every city can be reached by modern transport. Everything is connected, no problem. Okay, now comes the hard part of the lecture. I'm more than halfway through what I have budgeted. We now have to prove that we indeed compute the shortest paths with this algorithm. Actually, we compute the shortest paths. When I was running the algorithm through the example, I highlighted in red the selected edges. You can store those paths by maintaining an array with the predecessor vertex. So when you select a vertex for which the distance is minimal, you actually know also the edge that connect that new vertex to the set S. So you have an array where for every vertex you store the predecessor. If there is no predecessor, you just put -1. But just so at the end, you can actually you compute the algorithm then computes two arrays, the arrays with the distances and the arrays for the um, shortest paths. And actually, you can think about the shortest paths. There could be as many as you have vertices. This could be seen as a two-dimensional data structure that you need. But the point is that if you have this one vector, one-dimensional vector, you can actually reprint out all the shortest paths. And that's actually the next exercise. So this is a running of the extended algorithm of Dijkstra, where you are computing an extra vector with the predecessor for every vertex. So you show the evolution of this vector p, and at the end I want to show that you can interpret this vector p and actually list all the shortest paths from the source to the vertex. So in a way, you go through all the predecessors. So from V you go to the predecessor, which is U. For U you have a predecessor until you hit the source, which has no predecessor. Okay, so that's the last exercise, which exercise 5, which is very straightforward, I hope. So not all exercises are of the same difficulty. All exercises will receive the same credit. So in some sense, if you get stuck in exercise 2 or 3, don't get discouraged. Continue or start by selecting those exercises which you deem are easiest. Okay, so now we have to prove that the greedy algorithm, so Dijkstra's algorithm, is actually optimal, and it proceeds by incrementing that set S. So we will actually prove this theorem by induction on the number of elements on the selected vertices. Okay, the base case, we actually select neighbors, and indeed we actually add that neighbor to the source for which the length is minimal. So that's actually the shortest distance, indeed. So as the first step is fine. Now assume that at stage n, when we have already processed n vertices, so n is also the total number of vertices, but here n is just any local variable. So for if we have processed it for the cardinality of S, and cardinality of S is n, so I should actually not say that it is true for all the sets less than the current cardinality. We have the shortest path. Then we will have to show it that also for the addition of the new vertex, we have that the path that we compute is the shortest path. Okay, so we will do this by a contradiction. So we will add a new vertex and therefore also compute a new path, compute a new distance. Assume that if it's the minimal distance, there's nothing to do, but assume that it would not be the minimal distance, dv would be larger than the minimal distance, then it would mean that there is another shorter path from the source to that vertex. Now, since there is another path, and we have examined all paths that are connected from V to S with the shortest distance, so the other path that is shorter should actually contain a vertex that is not an S. Okay, there should be can be many, but assume that X is actually now the last vertex on this so-called shortest path called as P. It's not the one that we computed. And assume now the last vertex in S and the last vertex that is not an S. So we have X, the last vertex on the path, and then the next vertex not in the set S on the path. Okay, so by the induction hypothesis, so we have that because X is in S, the path that we computed to X is actually the shortest path from the source. So Y is not in it's on the path, but it's not in the selected set. What actually happens there is that because of that, the length we select V before we select Y. So that's actually the problem. So that means that the distance from X to the source plus the length of the edge XY must actually be larger from the distance that we have computed now. However, but Y is on that path, so actually it means that the length of the path to Y it's supposed to be the shortest path from the source to that new vertex V, but already when we hit Y, we are already at a longer distance. So we can't have that this path would be shorter than the path that we computed to V. So that's the contradiction. So if we have for all the shortest paths up to the cardinality of S, if we have all the shortest path there, we didn't make any mistake, if you like, the algorithm was correct up to then it's also correct for the next induction step. And that proves the optimality of this greedy algorithm. Okay, one last slide. What is the running time? So if we look at the algorithm again, the loop actually takes as many steps as the number of vertices. So that means that the loop is executed n minus 1 times, or order of n if you like. We consider all the edges, so that means that the loop actually has a worst case upper bound of order n times m, which is okay, which is almost a quadratic algorithm if the the total number of edges, is proportional to n, but it could also be a cubic algorithm, which is not really good. So if we have a priority queue to store the vertices, so that means that in a priority queue we have a key and we use the distance, so the vector of all the distances. So for every we store the vertices there, for every vertex we store the distance as the key. Then actually the running time can be improved to m times the logarithm of m. The logarithm of n is the depth of this complete tree, which is the heap or the priority queue. And the logarithm of n is also the number of operations that you need to do to update the priority queue. So, and then actually the worst running time is reduced by a significant factor. Then actually we run over all the edges and we can state that we do per edge logarithmic number of time of operations in the number of vertices. Okay, I hope that this clarifies things. The goal of the lectures is that you get to solve the exercises. So here are the 10 exercises which will be collected at the end of the third week of classes. The other goal of the lectures is that you find your way into the textbook. We are already now in the middle of the fourth chapter. If you have not started reading the textbook, then I would strongly recommend that you start doing this.